and left to reach equilibrium in a flask at a temperature of 550 Kelvin. The equation for the reaction between nitrogen and hydrogen is shown. When equilibrium was reached, the total pressure, so we've got the total pressure here, so this is our P total, was 150 kilopascals, and the mole fraction, so this is the mole fraction of ammonia, is 0.8. Now we know that all the mole fractions have to add up to 1. So our nitrogen plus our hydrogen plus our ammonia equals 1. And we know that the ammonia is 0.8, so we know that the other two must add up to 0.2 in total. Now it told us they were mixed in a 1:3 ratio. So in total there are 4 parts there, so 4 parts equals 0.2. So 1 part equals 0.05. So it means that the nitrogen is 0.05 and the hydrogen, 3 parts, 0.15. So these are the mole fractions. To work out partial pressure, we want to times each by the total pressure. So we do that on our calculator. We're getting 7.5 for the nitrogen, 22.5 for the hydrogen, and 0.8 times 150 is 120. And your double check is add up these 3 numbers and it should add up to the total pressure, which it does. Now it asks us to give an expression for the equilibrium constant. Remember that an equilibrium constant is a fraction and it's the partial pressures of the products. So we've got the partial pressure of ammonia, and we've got 2 moles of ammonia, so squared, over the partial pressure of nitrogen, we've only got 1 nitrogen, times by the partial pressure of hydrogen, and hydrogen's cubed. And the one thing that the examiner will be looking for here is that you do not at any point use a squared bracket which represents concentration. The second they see a squared bracket, you will not score the mark for a Kp expression. So we've now got in a different equilibrium mixture, this is just in case you got those partial pressures wrong in the first part, we have to calculate the Kp. So remember that we've just written the expression for Kp as partial pressure of ammonia squared divided by partial pressure of nitrogen times partial pressure of hydrogen cubed. So we're putting these in, 1.10 times 10 to the 3 squared divided by 1.20 times 10 to the 2 times by 1.50 times 10 to the 2 cubed. So you need to type this into your calculator. If you do that, I would start by pressing that fraction button that you have, use those brackets, use the times 10 to the button down at the bottom. Then on the bottom line, repeat that, remember, and to do to the power 3, you do x to the little box button and then you put the 3 in. And we've got 0.0029, goes 87, so I'm going to go 299 to 3 significant figures. So they've given their numbers to 3 significant figures. So I'm going to write my Kp value in, 0.00299. It now asks me to give its units. So bearing in mind that everything was in kilopascals and we had squared over kilopascals and kilopascals cubed. So that was the equivalent of having kilopascals squared over kilopascals to the 4. So with powers, we've got 2 on the top and 4 on the bottom. So we're going to subtract those powers. We're going to have kilopascals to the -2. The next bit asks us, the enthalpy change for the reaction is -92, and that is an exothermic, because delta H is negative, enthalpy change. State the effect of an increase in temperature. Well, when you increase in temperature, you're going to shift in the endo direction to absorb that heat, which is backwards in this reaction, which means that Kp, because we're going to end up with less products and more reactants, Kp will go down. So effect on Kp, it's going to decrease. So why is it going to decrease? So let's write down our thinking. The forward reaction is exothermic. That's just stating from the question. The information the question allowed us to interpret, forward reaction is exothermic. Next thing, when temperature increases, equilibrium shifts in the endothermic direction. To oppose the increase in temperature, always state Le Chatelier's, which is to oppose the change, in this case the increase in temperature. So Kp decreases.